Okay, welcome everyone to this webinar. Thank you so much for joining us. Today's webinar is EEG Decoding during inner speech using brain-machine interface. And our featured speakers today are Professor Kim. Professor Kim leads research initiatives. And these are brain-inspired AI, non-invasive brain-computer interface systems, and nonlinear time series forecasting through computational and data-driven approaches. His work focuses on neural signal decoding, explainable AI, and real-world decision to support applications spanning neuroscience, healthcare, and finance.
Thank you.
Additionally, we will have Hanbeot Park, who pursues research on brain-inspired AI models and brain-computer interface technologies through data-driven methodologies, specializing in EEG and neural signal decoding to enhance brain-machine interaction with a strong emphasis on real-world practical application. This 45-minute webinar includes a live demo and 10 to 15 minutes of Q&A at the end. So please put your questions into the chat and we will have a discussion at the end of the presentation. And now I will go ahead and turn over the discussion to Professor Kim.
Okay, thank you. Thank you so much. Hello everyone. I am Dr. Hoon-Hee Kim from the Brain Spider AI Lab at Pukyong National University in South Korea. First of all, thank you very much for attending today's webinar, and it's great pleasure to welcome such a diverse group of research and practitioners from around the world. So today, I'm proud to introduce our presenter, Hanbeot Park, one of the most talented researchers in our labs. He will be sharing our recent research on EEG decoding during inner speech using a brain-machine interface. This work explored how EEG signals recorded during the imaging or the internal speech can be decoded for downstream application, ranging from the device control to potential speech reconstruction. We will present the three key stages of this study. First, introducing inner speech task. Second, voice reconstruction using BEL EEG with dynamic time wrapping alignment. And third, decoding model without time alignment correction for image and speech. So we look forward to lively 3 or 40 minutes presentation and followed by about 10 minutes Q&A and discussion session. And also, since English is not our native language, please understanding if there are any smooth communication difficulty during the session. We are our best to keep things clear and engaging. We appreciate your patience and advance. Let me hand it over to Hanbeot Park. Please, your presentation. Begin your presentation, please.
Hello, everyone. I'm Hanbeot Park, researcher at BX AI Lab. In today's webinars, I will present our two-stage research journey entitled EEG Decoding during inner speech using a brain-machine interface. The content is as follows. In this presentation, rather than showcasing strong results from the outset, I will lay out step-by-step the sequence of methodological changes we introduced to overcome each problem. If you haven't encountered the term inner speech before, it refers to the mental act of producing words or sentences silently in your mind without any actual vocalization. Whereas motor imagery research focuses on imagining physical movements, for example, moving your arm or foot. Inner speech involves covertly speaking words or sentences in your head. An inner speech BCI could enable language-based interactions such as real-time speech synthesis, silently communication, or AI assistant control, or driven directly by brain signals. With the recent surge in generative AI research and development, many new generative approaches have emerged. In our study, we recorded brain signals using a BEL EEG system and applied generative AI to synthesize speech directly from the EEG data. When I say hello in my head, the system generates the audible word hello. Our main reference was her list paper toward voice reconstruction from each during imagined speech, and we adapted the network architecture illustrated there. Spoken speech EEG was collected while participants actually vocalized words, whereas imagined speech EEG was recorded during silent inner speech. We applied multi-CSP for domain adaptation and feature embedding, and trained a generator and discriminator pair with a GAN-like structure. A pre-trained vocoder produced waveforms, and a pre-trained ASR model converted them into text. Okay. After let's listen to the audio.
Help me.
This is original voice, and this is generated voice by imagined EEG speech.
Help me.
Yeah, after listening to the demo, we saw that the generated speech was impressively clear. So we decided to implement this approach ourselves. We follow the protocol outlined in the reference. Let's watch a short video. During the relaxed segments, participants simply rest without engaging in any specific thoughts. After they hear the target audio or sentence as an audio cue, each cycle consists of a fixation interval followed by a test interval signaled by a blue dot. And this cycle is repeated 4 times. So this is test time, and this is fixation time. With a BEL EEG system, we are able to maintain consistently low electrode impedance, and the resulting power spectrum density profile were clean. This setup let us acquire high-quality EEG data quickly and with minimal efforts. To build this dataset, we recruited 20 participants, men and women in their 20s, and asked them to produce 13 target words: ambulance, club, hello, help me, light, pain, stop, thank you, toilet, TV, water, yes, rest. Each was recorded with 113 channels at a 250 sampling rates. Each participant completed both the spoken speech and imagined speech tests, repeating words 48 trials for a total of 624 trials per participant. We followed the reference exactly, but we applied 30 to 120 Hz bandpass filter and notch filter at 60 Hz and 120 Hz to remove unwanted frequencies. Next, we use IC with IC label to take out eye blink and muscle noise. After that, we'll learn multi-class CSP, which make the spatial and frequency pattern for each word clear, so the EEG to BEL network can learn speech feature more easily. For domain adaptation, we train the CSP filter first on the cleaner imagined speech EEG, and then use the same filter on both imagined and spoken EEG, spoken speech data. We built a generator and discriminator pair based on the neural tone design. Its network is mostly made of one-dimensional convolution filter, and we added GRU to handle the time series data. The generator and discriminator have mirror image structures. Both models were trained with a mixed loss combined root mean square error, CTC, adversarial loss, and cross entropy. we extract the MEL spectrogram in the format required by the vocoder. We use HiPiGaN Universal Version 1 as the pre-trained vocoder, and the ASR component was built on a pre-trained Hubert model. Although HiPiGaN version 1 was never trained on our participants' MEL spectrograms, it will deliver excellent performance. One reason it is so widely adopted in other studies. Because imagine speech EEG has no pair target MEL spectrogram, we adopted a transfer learning strategy. We first trained the model on spoken speech EEG, then fine-tuned it on imagined speech EEG using the voice recorded during the spoken speech trials as the target. For proper alignment, we asked participants to begin the task immediately when each task interval started. This audio is oh, okay. Let's listen to the audio. And then the system ended up generating very noisy and unintelligible speech. Nevertheless, the low root mean square error indicates that although voice generation was difficult, but classification might still be viable, so we shifted our focus from the voice generation to classification. Because the Fisher ratio is widely used for the feature extraction in motor imagery EEG, we hypothesized that it could also highlight the most discriminated region of a MEL spectrogram. To build a MEL spectrogram classifier, we first augmented the speech data to 1,000 samples per class, then computed the Fisher ratio across the spectrogram and selected the 10 highest scoring feature for training. Here are the Fisher ratio results. Because each class displays clear, distinctive pattern in the Fisher ratio map, we conclude that classification should be feasible. We augmented the speech data 1,000 samples per class, then computed the Fisher ratio across the spectrogram and selected the 10 highest scoring feature for training. Using an MLP and SVM yielded average reference score of 0.7 and 0.83 respectively, still below the threshold we considered acceptable for a practical classifier. To overcome this, we augmented the voice data and treated each MEL spectrogram as an image, using ResNet 18 as the classifier. We achieved almost perfect performance. So consequently, we replaced the vocoder and ASR model in the original pipeline with this pre-trained classifier and trained the generator and discriminator around it. We replaced the original word list with 10 commands specifically selected for controlling electronic device. Turn, on, off, camera, left, right, receive, call, message, music, volume, up, down. As a result, most participants achieved F1 score of 1.0. The root mean square remained very low, and the model conversed remarkably quickly. However, the near-perfect classification for almost every participant made us skeptical, and we eventually realized that the reference implementation cannot generate voice using EEG data alone. However, to correct the time-axis distortion in the generator's MEL spectrogram and fix their scaling, we had to apply DTW alignment and denormalization. DTW alignment is providing the EEG for the imagined world on, together with its target mass spectrogram, enables us to correct the temporal misalignment between the generated and ground truth mass spectrogram. And denom is the generator outputs a normalized mass spectrogram. During denormalization, we reconstructed the original scale using the class-specific, for example, on, mean, and standard deviation. Both of each require a ground truth mass spectrogram. This meant the system could not rely on EEG alone. Without DTW and denom, classification performance to F1 scores between 0 to 0.1. So we needed a different solution. We proposed three potential fixes. First was changed feature extraction method. Second is change generator network. Third is generator DTW denom, or eliminate. As an initial experiment, we eliminate the DTW and denormalization step and swapped the neurotalk generator for an ESN-based model, raising the number of multi-CSP segments from 16 to 172 to accommodate the ESN's operating schema. Because the DTW and denom were gone, the generator now had to correct its own time wrapping and mail scaling errors. So we turned the ESN's hyperparameter extensively to address these challenges. We tuned the ESN's hyperparameter intensively using a genetic algorithm, a nature-inspired optimization method to handle these issues. Yeah, let's listen the audio, but this audio will be, we cannot listen, this audio is cool. So the performance remained poor and the generative speech was very unintelligible. To address this, we replaced the ESN with Mamba, an architecture proposed as a transformer alternative in NLP tests, but its performance was likewise unsatisfactory. We observed that the mass spectrogram produced by the generator differed completely from the target's, both in their internal detail and in their overall shape. Dividing a 2 seconds with window into 172 segments leaves only about 11.6 milliseconds per segment. It's far too little information. To make sure each EEG input covered at least 0.5 seconds, we switched from fixed segment to a sliding window approach. We also replaced standard DTW align with a differentiable soft DTW loss. The model's mass spectrogram looked very different from the real ones, and the classifier still did poorly. Its F1 score stayed around 0.1 to 0.2. This audio will be, it is very similar with music, but other voice was not. So when we played back to the generated voice, a few words occasionally sounded similar, but they weren't accurate. Interestingly, we sometimes found that the generated speech sounded more human-like when the generator loss was not fully stabilized. Since CSP used a feature extraction method in motor imagery studies, We instead considered filter bank features, power spectral density, and low EEG for the imagined speech task, and evaluated ESN, Mamba, and transformer architecture as candidate decoders. We included Mamba and transformer as decoder candidate because both have already shown outstanding performance in NLP and other sequence processing tasks. And Mamba, in particular, offers lower computational complexity, enabling faster training and inference. While exploring ways to improve performance, we reviewed the Cerebral Voice paper presented at ICLR 2025. Although the study decodes equal rather than EEG signals, its proposed architecture performed exceptionally well. After analyzing their TTS-based model, we decided to integrate each of our candidate core model into that framework for further experiments. This diagram illustrates our latest end-to-end architecture. Compared with the previous version, we have removed both the discriminator and domain adaptation block, and we have reinserted the vocoder and ASR module in place of the pre-trained classifier. The resulting design is much simpler and lighter, making real-time inference a realistic option. Here are the results using a raw EEG with a TTS-based transformer. You can see that these mass spectrograms are almost same, so voice will be very same as you hear. All classes produced almost identical speech, so we had to revisit the problem.
Camera. Tone. Message.
Because the BEL EEG system offered no built-in way to send real-time annotation from the protocol computer to the BEL EEG computer, or to capture CPU timestamps, we instead logged label and timestamps according to sampling rate and segmented the voice and EEG data on that basis. Later, we discovered that the voice clip had not been cut correctly and realized that the EEG segments were likely misaligned as well. Accordingly, we sent trigger signal from the local computer via USB to serial to generate annotation, logging both the CPU timestamp and the label in real time at the start and end of each segment. We also accounted for the delay between pressing record button and the actual onset of recording. This approach let us segment the audio precisely, and calculation based on sampling rates showed that the EEG segments were now accurately aligned as well. We selected the training words and sentences by choosing expression commonly used in everyday conversation. Using the neurally segmented EEG as input, we trained the TTS-based model. We intentionally elongated each word pronunciation so the generator could clearly distinguish single word from full sentences and avoid mixing them up. For example, is go and go to school. The results are shown below. Unlike our previous attempts, the predicted MEL spectrograms now closely match the target MEL spectrogram. So as you can see, this MEL spectrum is very same as target and predicted spectrogram. This is a simple demo page. if I go to this webpage, can you hear this voice?
Go. Go to school.
Go to school.
Home.
Home.
I am home.
I am home.
Time.
Time.
Today.
Today.
Today is Sunday.
Today is Sunday.
Wait.
Wait.
Wait a second.
Wait a second.
What time is it?
What time is it?
Okay. This evaluation metric, we use CR and L1. So CR is computed by comparing the text produced by the ASR model with the target text. And L1 is the mean absolute error calculated frame by frame between the predicted mass spectrogram and the target mass spectrogram. Both the CER and L1 metrics are also low. This demonstrates that beyond the choice of EEG decoding method, precise timing and segmentation are absolutely critical. Unfortunately, the BEL EEG system still lack real-time streaming, such as a lab streaming layer. So we cannot immediately decode the participant's inner speech to deliver fade-in feedback or generate speech on the fly. Once real-time streaming is added, both feedback training and real-time voice generation should become feasible, and we expect the system performance to improve significantly.
Turn on camera. Turn off camera. Turn left. Turn right. Receive call. Receive message. Turn on music. Turn off music. Volume up.
Finally, here is a brief introduction to the Brain XI team. My name is Hanbeot Park, presenter, member of the BCI team, responsible for BCI decoding algorithm and brain-inspired AI. Hoon-Hee Kim, advisor, assistant professor, Department of Computer Engineering and Artificial Intelligence. Tae-Woon Lee, member of finance team, focused on time series data and brain-inspired AI. Yoon-Jung Cho and Hira Chung, member of the BCI team, responsible for neural signal and analysis and machine learning. Oh, thank you for listening, and let's Q&A.
Great. We do have some questions in the Q&A. And please go ahead and add questions to the Q&A and we'll answer those from there. Did the participants have difficulty understanding the instructions for silent speech? Did they move their lips while imagining speaking?
Let me answer this question. So, uh, our instruction to the subject to the instruction is very clearly don't move your lips and don't move your any kind of your muscle, just imaging your just speaking your word or just talking. So it is not difficult to understand in the instruction for silent speech to the participation. So it is very clearly and controlled these protocols. Is that it is very clearly is a very important part about this study because some Muslim movement can make some easy signal to and maybe we are just decoding the just the muscle signal, but we decoding the inner speech very clearly. Okay.
Yes.
Okay.
Do you think the feature extraction and prediction could be improved by using EEG source localization of the signals to the person's cortical surface?
Yes, there are already several studies on inner speech that use invasive system capable of direct recording from the cortical surface, such as ECOG systems. This study often referred to significantly improved features extraction and decoding performance, largely and because performance and because the spatial resolution and signal to noise ratio are much higher than with non-invasive EEG. So it's a very significantly improved research result. Uh, and and especially study using ECOG, ECOG have shown promising result for inner speech decoding. So ECOG provide a high spatial, or already said that the high spatial and temporal resolution, and it allows for more precise localization of neural activity on the cortical surface. Okay, is
Great.
it? Yeah. Okay. Okay. Let's move.
Uh,
Uh, and earbud. Oh,
so once the feature extraction has been learned with the adjusted time course, do you think the input EEG could be scanned to flexibility estimate the time of onset and duration of the features?
mm, mm, Actually, this study is a very early stage, so I can not sure about this model can handle the flexible situation. So maybe some calibrate maybe we can calibrate our model and this model can extract the feature and adjust the time course. Maybe it can. Maybe I cannot sure about that.
Oh, understood, understood. Um, did you try to restrict coverages to specific areas, temporal frontal areas? How many electrodes are actually necessary for decoding?
Actually, this is a very important picture about the brain-computer interface systems because normal subjects need some low-cost EEG system, but unfortunately, we are not tested about the limitation about the channel number. So, but I'm not sure. I'm not clearly answered that these questions, but I can. But some previous studies show the prefrontal cortex signal is very important to decoding the inner speech system. Okay. Uh, can I just close and comment to this webinar?
Of course.
Okay, thank you. Thank you for your attention to our presentation. So, but some technical issue in the sound problem. So, but you can just connect our GitHub. The GitHub address is provided this slide. So, you can hear the original audio from the subject and you can hear the EEG image and the audio. So they are very similar to the sound in our systems. So this is a very main founder about our research. And and thank you for your attention. And we are improved our research to very highly level of the brain-computer interface system for the decoding the inner speech. This is our future plan. And also thank you for Hanbeot. Your presentation is very thank you for your presentation. So do you have any comment about the end of this closing? Do you have it? No? Are you hear that? Okay. Thank you for your presentation. It is that's it. It is the end of my comment. Thank you for okay.
Thank you so much. Thanks everyone for joining.
Okay.